Hi everyone, I'm Alireza Shefaei, PhD student at TU Delft. I work on multi-objective stochastic storage planning with considering the uncertainty of the demand and rainfall. In response to the high demand and also the climate change-induced impact, the water utilities impose the large consumers to restrict their water. In response to address this issue, the rainwater harvesting systems can be an option in addition to the input from the network. By it, planning depends on the uncertainty of the demand and also the rainfall. The literatures in this topic mainly worked on use the simulation-based optimization to solve this problem, to find the optimal storage size. But their work has some drawbacks such as interactability or low efficiency and so on. And also, they did not consider the uncertainty in their work. In this work, we want to cover these issues. As they start, for considering the operational routes, the flows in the network, we consider the mainly used yield after spillage method, in which you can see the different flows, for example, runoff, the outflow, and the volume of the storage in the network, and S represents the storage size. But the min and max operators in these flows make the problem highly non-convex, and we could not solve this problem to optimality. So we use the big M method, and by introducing binary variables, reformulate the non-convex problem to a set of mixed integer linear equations. And then we formulate the problem in single objective options by maximizing the efficiency, which is defined as the outflow from the tank to the network over the demand of the network, by considering the budget on the cost, and also from the other perspective, minimizing the cost of planning by considering a minimum efficiency for the system. And also we can formulate the problem as a multi-objective by considering both of the objectives simultaneously. So we can introduce the uncertainty in the network, in the problem, by considering the rainfall and demand as the random variables, that their historical data follow a specific probability distribution. By doing this, we can formulate our stochastic multi-objective problem, in which instead of the efficiency, we calculate the expected efficiency over the demand and rainfall scenarios by considering the constraint, the flow constraint. And also, if we want to have a guarantee against the worst scenarios, we need to use a risk measure, in which we use the CVAR, the conditional value at risk, which is a commonly used risk measure in the operational and planning problems, in which the decision maker add a value of the risk to their objective function by beta parameter and adjust the percent of the worst scenarios using the alpha. And considering this optimization problem, we can reach to a risk-averse stochastic plan for our rainwater harvesting systems. As the coding in the Julia, we read the data using the delimited files package. Then we define the parameters and initialize them, and for changing between the risk neutral and risk averse, we change the beta parameter to 0 and 1 respectively. And then we import the required package, which is the jump and multi-objective algorithms package. And then we define the planning variables, the binary and control variables, which are depend on our rainwater, on the demand and the climate scenarios, and also the seaware-related variables, and then defining the constraints, the set of mixed integer equations as these constraints, and then defining the objective function, the multi-objective objective function as a set of vector of objectives. Using this objective, we use the vector to input the multi-objective problem. Then, and our case study area is a botanical garden in the Amsterdam that we use the data of this area. By solving the deterministic problem in the single objective case, for the maximizing efficiency, we got the high efficiency, but by paying the high amount of the cost. But when we minimizing the cost, we need to pay a little amount of the cost, but we have to expect a little value of the efficiency. But as the scenario, as the input of our stochastic problem, we need to generate scenario. For this purpose, we use the KNMI data and apply their different uncertainties about the temperature, level of sea airflow, and also different level of uncertainty. We generate our rainfall scenarios. And in this figure, you can see the range of our demand and rainfall scenario and the deterministic value that we use as input to generate these scenarios. As this result represents our stochastic programming for minimizing the cost, considering a minimum value for the efficiency. As you can see, we get a higher efficiency in the risk averse and risk nuclear compared to the deterministic case when we consider the worst case scenario and 8 of the worst scenarios. And also, when we solve the multi-objective optimization, we get a similar result. For example, this, as you can see, this figure also follow the result of the previous table. For example, for the 8 worst scenarios and for the worst year scenario, we have a higher value of the efficiency when we solve the risk averse and risk nuclear compared to the deterministic one. As conclusion, the contribution of this work converting the non-convex flow equations to the mixed integer linear programming and for providing a trade-off between the efficiency and cost, and also considering uncertainty of the rainfall and demand in the rainwater harvesting systems design, and also again the worst case scenarios using a risk measure. And also as a future direction, we can consider the impact of the price of water and the water quality issue, for example, defining different index for assessing the quality of water, and also reducing the computational burden of this problem using the different approach, for example, the composition approach. And thanks for consideration.
Okay, are there any questions? I think we have time just for one quick one, but yeah.
Hi, thanks very much for the talk. I was wondering, because basically in many European cities, you have much more precipitation in winter than in summer. So how do you take that into account? How much does that affect the solutions to your problems?
For this scenario generation, the KNMI data has 2 different scenarios, one for over all of the year and one for the winter season.
Okay,
and
so you separate out the winter season. Okay.
2 different scenarios for the over all of the year and the winter.
Okay, thanks again. And I think we can go to the next speaker. Thank you.
Welcome.